Okay, welcome to 150, section 2, lecture 27. And so what we're going to do today is we're going to do TaylorSeries. So TaylorSeries is one of the most important parts of the course. It's one of the things that you are more likely to do. The idea is to take a complicated function and replace it with a simple function. And what we're going to do for our choice of simple functions here is to use polynomials. You could use other types of functions. You could use trig functions, use sines and cosines. This leads to Fourier analysis. You could use wavelets. You can use other bases of functions. This is the first part of a very huge story. One of the bonus lectures you can watch is on streaming video. How do we transmit information quickly? Streaming video is significantly better from the early days, and I remember the frustration of just things hanging up. How do you transmit this much information this quickly? We've now reached a point where it'd be fascinating to know how many DVDs and Blu-rays you all own versus how many services you subscribe to that you can just access on demand anywhere you want. So what's TaylorSeries? So the idea is to use some information about the function to build up approximations. So if you could have only one piece of information about the function at a point, what would you choose? It's notation. So you would choose, say, f of 0. You can adjust it to be another. And then if you could have another piece of information, what would you choose? F prime of 0. Now, something you could do instead of f prime of 0 is you could look at maybe f at another point. And maybe I'll evaluate f at two nearby points. And you could continue. And after we know f of 0 and f prime of 0, the next thing is to look at maybe the second derivative, f double prime of 0. And then f triple prime of 0. And then, fortunately, it's very rare in the standard sciences to need to go beyond the third derivative in the equations. You study Newton's equations. These are second-order differential equations. But occasionally, we do need more derivatives. Sometimes they switch to Roman numerals. Sometimes they switch to numbers in parentheses. I'll use the number in parentheses mark. 4 of 0, and so on. And the idea is you want to build up a polynomial to approximate your function using this information. And so the nth order Taylor series at 0 would just be the sum that goes from 0 to n of the kth derivative of 0 over k factorial times x to the 10. Or f of 0 plus f prime of 0 x plus f double prime of 0 over 2 factorial x squared, all the way up to the nth derivative at 0 over n factorial x to the n. And the hope is that this will converge, and moreover, it will converge to the original function. It will happen occasionally that the Taylor series converges and goes to infinity to something other than the original function. And that just shows you that the subject is painful and that it really is a job for pure mathematicians. What do you do in a situation where it converges to something else? Fortunately, most of the time it will converge to the function that you want. And so one thing to notice is that this is set up so that the derivatives match. So if I take the value of the function of 0, I get f of 0. If I take x equals 0 over here, everything vanishes but f of 0, and so they agree. If I want to look at the first derivative, I take the first derivative of both sides. So this is a constant, so it vanishes. The derivative of x is 1. And then every term here has at least an x squared. So when I take one derivative, they'll also have an x. So when I take the first derivative and put x equals 0, I just get f prime of 0. Oh, good. If I take two derivatives, these two terms vanish. Everything x cubed and higher vanishes at 0. And then x squared, when I take two derivatives, it's going to be 2 times 1. Oh, good. That 2 factorial cancels the 2 factorial. And I get f double prime of 0. So with a little bit of work, you can see that this polynomial, its derivatives up to n, agree with the derivative of n here. Yeah.
So like when you go to like the third or the fourth term, I guess, like where does the 2 come from in the 3 factorial?
Well, the next one would be x cubed would be f triple prime of 0, x cubed over 3 factorial.
Yeah. So then when you take the derivative of it, it's a 3 would cancel out.
Well, what would happen is if I give you, say, the term x cubed over 3 factorial, when you take its first derivative, you get 3x squared over 3 factorial. When I take another derivative, you get 3 times 2x over 3 factorial. And when I take one more derivative, you get 3 times 2 times 1 over 3 factorial times 1. And so when you take enough derivatives, this is going to perfectly balance that into 1.
Thank you.
What if I were to take n plus 1 derivatives? What would I get if I take n plus 1 derivatives? So if you take 3 derivatives of a quadratic, what do you get? So quadratic would be ax squared plus bx plus c. If you take one derivative, it's 2ax plus c. If you take 2 derivatives, it's 2ax, so it's just 2a. If you take 3 derivatives, it's 0. If I take 3 derivatives of a quadratic, it's 0. What if I take 4 derivatives of a cubic? What is it? 0. If I take n plus 1 derivatives of a polynomial of degree n, it's 0. So it can't match forever unless your original function has all of its derivatives 0 from some point on. So up until degree n, it's going to match at the origin. But beyond that, you expect it to start breaking down. Instead of doing it at the point 0, I could do it at the point 5. I would just do x minus 5 and just shift things over. But just for ease of writing. So we can now calculate the Taylor series of some common useful functions. So really important ones, cosine of x is 1 minus x squared over 2 factorial plus x to the 4 over 4 factorial minus x to the 6 over 6 factorial, and so on. Sine of x is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. E to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and so on and so on. Now, something that's really worth noting is e to the ix is cosine x plus I sine x. So here, I is the square root of -1. So I squared is -1. So I to the 4th is 1. This is an extremely useful relation. And if I just plug in for x, I times x, notice that when x is to an odd power, we're going to have I to an odd power. When x is to an even power, we'll have I to an even power. Every time the power of I increases by 4, you get back to 1. I squared is -1, I to the 4th is 1. What's I to the 5th? I to the 6th. -1, because I to the 6th is the same as I to the 4th times I squared. So I to the 6th is the same as I squared or -1. So if you put in ix, you'll see that all the odd terms are going to give you I times sine. And the even power terms are going to just give you cosine. So this is an extremely useful relationship. Other important ones are the Taylor series for the log of 1 plus x and the log of 1 minus x. So this is equal to negative x plus x squared over 2 plus x cubed over 3 plus x to the 4th over 4, and so on and so on and so on. So we'll actually prove that this is correct in a moment. It's worth comparing the different formulas here. Which do you think is going to converge faster? The Taylor series for the log of 1 minus x when x is near 0, or the Taylor series for say cosine, sine, or exponential? Which do you think converges better?
Exponential.
Why?
I don't know, because there's too many like changes in sine and cosine.
Well, changes in sine might actually help you with some cancellation. But of course, if So the exponential does converge faster. What's the difference when you look at the coefficients over here for the exponentials and the cosines and sines versus here? So the coefficient of x to the fourth is just 1/4. Here it's 1/4 factorial. You've got factorials down below. It's not a coincidence that the last lecture we talked about how fast the factorial function grows. The faster the factorial function grows, that means the larger we're dividing them. And thus we're dividing by huge things, so we expect that the terms further and further down will contribute less and less and less. So because the factorial is growing so rapidly, these converge very quickly, while the one for the logarithm converges much slower. So let's actually prove the claim for the log of 1 minus x. So we'll have f of x is the log of x. So the log of 1 minus x. And we're going to look at x near 0. So we're doing a Taylor series about 0. Well, let's imagine x is a small positive number. What's the log of 1? 0. So we know f of 0 is 0. If I take a number less than 1, is the log of a number less than 1 positive or negative? Negative. And if you look at the expansion for the log of 1 minus x, it will be a negative number if x is positive. So that at least passes your quick test. So let's start calculating derivatives. What's the derivative of the log of 1 minus x? Yep, and I'm going to write that as 1 minus x to the negative 1 times negative 1. So it's 1 minus x to the negative first power, and then the derivative of 1 minus x is negative 1. Okay, so what's f prime of 0? Just negative 1. Let's calculate the second derivative. Now I would have negative 1 minus x to the negative 2 times negative 1 from this, and then another negative 1 from the derivative. Or if you want, when the negative 1 comes down, the negative sign cancels this negative sign, but then I get another negative sign from this, so it's going to be 1 minus x to the negative 2 times negative 1. And what's f double prime of 0? Negative 1. And so do you agree that all the derivatives of f are going to be negative 1 at 0? No, two data points, right? You know, this is not enough of a pattern to be confident. There's a beautiful polynomial where if you evaluated the integers 0, 1, 2, all the way up to I think 41, it's a quadratic and it's prime for those first 41 values, 45. And then it starts being composed. You know, strange things can happen, patterns can go on for a while before they break down probably. So just because it starts off negative 1, I'm not comfortable yet. Let's do a little bit more. At triple prime of x, I'll have negative 2. So the negative cancels with the negative 1, so it'll be 2. 1 minus x to the negative 3. And then the derivative of this is always my negative 1 again. Now I get f triple prime of 0 is equal to negative 2. Or maybe it's just a negative Fibonacci. Still too many possibilities. Let's take the fourth derivative. What's the fourth derivative going to be? Negative 6. So it's going to be 3 times 2. The negative cancels the negative 1. 1 minus x to the negative 4. And then the negative 1 from the chain rule. So how should I write the fourth derivative? How should I call that number?
3 factorial.
3 factorial. Negative 3 factorial. How should I view this over here? It's 1 times that. So when the negative 1 came down, there's really a 1 there. And if I keep that 1, you can see that these are factorial. And so if I now look at the kth derivative as 0, it'll be negative k minus 1 factorial. And so now if I start trying to expand things, I would get the sum, it goes from 0 to n, of the kth derivative at 0 over k factorial times x to the k. And this will be my nth order Taylor series of 0. Now, we have to be careful. It's k minus 1 factorial, so long as we're starting off at the first derivative. When k equals 0, when we don't take any derivatives, the value is just 0. So this is going to be the sum, k goes from 1 to n, of negative k minus 1 factorial divided by k factorial x to the k. Well, what's k minus 1 factorial divided by k factorial? It's just 1 over k. And that's exactly what I claimed we have. So this is how you would actually compute the Taylor series. You would just keep taking derivatives like this. If you had to do sine or cosine, what you would notice is sine and cosine, the derivatives are periodic with period 4. The derivative of cosine is minus sine, derivative of minus sine is minus cosine, derivative of minus cosine is sine, and the derivative of sine is cosine. Every 4 derivatives returns you to where you start. Why do you think it's 4 derivatives that return us to where we start with sine and cosine? What do you think is related to that that also has some kind of periodicity with period 4? All right, it's related to I. All right, so what I want to do now is I want to switch and show some plots of Taylor series. And so hopefully the video should be working. Okay. And so I wrote some mathematical code that allows me to plot cosine and plot the Taylor series of order n, draws a, we'll call that orangish brown line. And you can choose where the point is. Now, I also have this parameter C that allows me to zoom in and zoom out. And so I can zoom in a little bit and see what's going on. And right now I am doing the first order Taylor series, n equals 1. Although really, the first order and the 0th order Taylor series are going to be the same because cosine is 1 minus x squared over 2 factorial. There's no linear term for cosine. And because there's no linear term for cosine, it's interesting. It seems to be some kind of psychedelic cascading waves in zoom land. We'll see if it gets better if I move out of the way. Oh, yeah, you can actually see it going on up close to it. Doesn't seem to get better as I'm going out there. I feel like we need a strange soundtrack for this. All right. Strange. So anyway, the 0th and the first order Taylor series are going to be the same at the origin, but if I move my point x naught, then I can see it changes, the curve changes. I can increase the degree, and this is looking at a degree 2 Taylor series expansion. I'll zoom in a little bit. Cosine is periodic. I only have to study it from minus pi to pi to understand it everywhere. And if I look at this plot, we can see, well, let's see, pi halves is a little bit more than 1.55. So it's not so bad all the way up between minus pi and pi, or minus pi halves and pi halves. Up to plus or minus 1, it's actually pretty good. If I increase to a Taylor series of degree 4, zoom out a little bit, it's actually pretty good up to a little bit further. Now we know that these polynomials can't be perfect in the end because a polynomial of degree 4 is going to be going off to infinity or negative infinity, depending on those coefficients. But as I take more degrees, this is a degree 6 polynomial, it's now fitting beautifully beyond minus 2, 2. In fact, it's fitting so well, rather than plotting the function and the yes, I should actually plot the difference and look at how much are you off by. Because if I am much better into small values of x over here than I am over here, the fit is so good, I can't see that. I can't see if the error is 1 part in 100 over here and only, well, let's say 1 part in 1,000,000 here and 1 part in 100 over here. The scale is not going to be appropriate for seeing something like that. And if I take, even more terms, if I take degree 8, I can't even see a difference now. I have to zoom out a little bit. And, at this point, I'm going beyond minus pi pi with a polynomial just of degree 8. So it's remarkable how fast it does. And because so many of the terms are 0, we only have to worry about the terms of even degree. We don't need that many terms to approximate cosine beautifully. If I go up a little bit more, great fit, and I'll zoom out. So if I zoom out, you get some trouble. If I increase the degree a little bit, here I'm doing a polynomial of degree 20. Yeah, let's do 22. And I've got to zoom out pretty far before I start to see some difference. If I go even higher, here I'm at now around degree 40. It's a nice exercise to figure out just how many cycles of cosine you get, depending on what your degree is. But we're able to get a remarkably good fit for cosine without too much trouble. And this is, again, the power of Taylor series. So the code is on the homepage. And then, of course, I can shrink back the degree. I'll zoom out a little bit. And then you could see, so this is now going to be the best polynomial of degree 4. I can change the point. And as I change my point, you can see how things change and how the best polynomial changes. It does a beautiful job. Okay. The next is one of the strangest functions in all of mathematics. E to the negative 1 over x squared if x is not 0, and 0 if x is 0. If you look at what goes on as x gets larger and larger and larger, you're getting e to the negative 1 over a large number. So it's basically e to the negative 0. What's e to the 0? 1. And you can see that the function is approaching 1 as x gets further and further away from 0. Now, what happens as x approaches 0? Well, you have e to the negative 1 over x squared. If x is 1/10, you have e to the negative 100. If x is 1 over 100, you have e to the negative 10,000. This function is crashing down. When you look at this, I can't really see what the hell is happening over here because of the scale. This is another cause for why we want to understand logarithms, which will be the lecture on Monday, so we can figure out a better scale to use to study this, a better way to present the data. And so I'm going to zoom in a little bit, and I'm zooming in now, looking at it from like negative a half to a half, and you really can't see the difference between the function and 0. I'll zoom in a little bit more, and it starts to get absurd. We're talking now size of 10 to the negative 11, and that's still way too much to be seen over here. Zooming in a little bit further, or no, it's about as far as it will. I can probably cheat a little bit. And put like a 0 over here just to really like overflow it. Yeah. At this point, it's not happy. So here at negative 0.15, it's 10 to the negative 29. At negative 0.1, it's 10 to the negative 63. It's just dropping so rapidly. This function is terrible from the point of view of Taylor series. Using L'Hopital's rule, an extra credit problem early in the semester, was to show that all of its derivatives at 0 are 0. What does it mean for all of the derivatives to be 0 at 0? Well, fortunately, we should still have the Taylor approximation on the board. And so if you look at the Taylor series, if all the derivatives are 0, then the only term that survives is f of 0. So your Taylor polynomial is always going to agree with your original function at 0 for a trivial reason. It has to. But because all the other Taylor coefficients are 0, the Taylor series converges to the function that's identically 0. And that's not the same as the function we're looking at. We're looking at the function e to the negative 1 over x squared, if x is not 0, and 0 if x is 0. This is a truly strange function. If you extend to complex math equal x plus iy, you could look at the function e to the negative 1 over z squared. Well, if you take y equals 0, if you go along that path, it's e to the negative 1, it's the function we just had a moment ago. If instead you take x equals 0, you take 0 equals iy, you come down along the imaginary axis, you have e to the negative 1 over iy squared. What's I squared? So you have e to the 1 over y squared. Oh, it's going up to plus infinity. So along the y-axis, the function is coming to plus infinity. Along the x-axis, it's coming to 0. I don't even have to worry about taking the derivative of this as a complex value function because it's not even continuous. So we talked earlier in the semester about what does it mean for a function to be differentiable. It's not enough for the partial derivatives to exist. We needed the partial derivatives to exist and to be continuous. So for this function here, it's even worse. The function itself is not even defined. It turns out a complex differentiable function has a tremendous wealth of properties that a normal differentiable function does not have. And so when we try to do Taylor series, the theory is a little bit more involved. It's not enough to show that the Taylor series converges. We want to show that Taylor series converges to the addition function. And there's a lot of theorems you can prove that say if the function is differentiable to a certain degree, how well will it converge? And you can prove results along those lines. But I wanted to show the function just as a warning of how careful you have to be. Okay. Any questions on what we've seen up till now? So possibly in the Monday review class, we will do a little bit on the birthday problem. Anybody know the birthday problem or the birthday paradox? This one? How many people do you need in a room if you assume birthdays are uniformly distributed across the year before you have at least a 50% chance that 2 people share a birthday? It's only a little bit over 20. I remember, 1 year at Windows on Williams, I got permission from admissions that everybody at my table would have free admission to Williams if there were not 2 people at the event who shared a birthday. I had to promise to pay 10% of all the tuition for students at the table, but the admissions went along with it. There were over 100 people, 100 students at the event. The probability, which we'll see later, is so high that I was not worried. The students were very excited and started going from table to table, and they didn't even have to go with even complete 2 full tables from us before they had 2 people to share with them. And I did disqualify them, just to be clear. It's a painful calculation to do it exactly, but if you use Taylor series, you can actually estimate the answer extremely well, extremely quickly. And that's one of the key ideas behind it, is rather than working with the exact function, it's frequently easier to work with a close approximation. Now, we need to do multivariable Taylor series. So I'm going to give you some function of x and y. And we want to write down its Taylor series. So I'm going to first show you the correct way, which is painful to do in general, and gets worse the more degrees you have and the more variables you have. And then I'm going to show you a trick, which is sadly not taught that often, which will allow you to do almost every multivariable Taylor series you need quickly and easily if you know one-dimensional Taylor series. And this is, a common theme of the course. Mathematicians are lazy. Whenever possible, whatever you're given, reduce to an easier problem that you already know how to do. So, what do you think the first term should be in the Taylor series approximation? How should we start it off? We should start off with, it should start off with f of 0, 0. I think we should have the linear terms, the terms involving just x and y. We're trying to write this as a polynomial. What do you think the coefficient of the x term should be? Close. The gradient is the vector. What should be the coefficient of the x term? You want the derivatives to match up. I'm sorry?
Gradient at 0.
The gradient at 0 is still going to be a vector. I want just the x component. There's also going to be a y component. The partial of f at x. at 0, 0. Plus the partial with respect to y at 0, 0. And you can view this term as the gradient of f at 0, 0 dotted with x, y. You can use it. And now if I take the partial of both sides with respect to x, this will vanish, that will vanish, that will give you the partial of f with respect to x at 0, 0. It's going to agree. Now I have to look at the degree 2 terms. So the degree of a term is just the sum of the power of x and the power of y. If I have 2 x's and 3 y, it's going to be degree 5. If I have 6 x's and 1 y, it'll be degree 7. So what are the possible degree 2 terms I could have?
X,
Okay, so I could have x squared. What else could I have?
x1.
I could have xy. And what else could I have? And so I want the derivatives to match up. So what do I want is the coefficient of x squared?
With respect to x, and then with respect to x again.
Yep, so it'll just be fxx at 0, 0. And then this would be fxy at 0, 0. And this would be fyy at 0. And this is slightly off. And the reason it's slightly off is if I take 2 derivatives with respect to x, everything vanishes except for this term, but I get a 2 factorial that comes down. So what do I have to divide that by? 2 factorial. And now when I divide it by 2 factorial, it will match 2 derivatives of this with respect to x. I simply have to divide this by 2 factorial, but I don't have to divide this term. And then you can start writing down what would be the third order. Well, then I would have to have fxxx, fxxy. One way to view this, if you want, is this is maybe fxy plus fyx over 2 factorial. If we're assuming that the derivatives are continuous, then I can interchange the order of differentiation. And that's where the extra factor of 2 goes. I can write this in matrix form. So fxx, fxy, fxy, fyy, xy, xy, 1/2. And this is called the Hessian matrix. It's the matrix of second partial derivatives. And that's what corresponds to here. If I have more, yes.
How come it's written as like the TaylorSeries and fxy if we're doing it at 0, 0? Is it not another?
No, this means the partial with respect to x.
No, like up here.
Over here?
Yeah, I thought it's like xy if we were doing it at 0.
Oh, no, because we're evaluating the Taylor series at xy. In terms of what we did, oh, sorry. There's a bad typo. What should the 0 be? It should be x. So this is the Taylor series at the point x. Right. So what we're doing is, this is a function of x. So you give me a different value of x, and it's going to give me a different approximation to the original function. Right? And so the question is, how do I denote where the Taylor series is happening? And so I could put in some additional notation. I could put n comma 0 to remind me that this is the Taylor series at the point 0. I could do n comma 5 if I want the Taylor series of 5. We frequently assume that the Taylor series is being done at 0 just for convenience. But there are some functions where you will do it in different places. But since this is a function of x on the right-hand side, there should be an x somewhere on the left. Sorry about that. Okay, so now if you just do the algebra out, the matrix acting on a vector, within a vector over here, it turns out it equals the same as this. What class would be really useful to have right now? Linear algebra. So in linear algebra, there's a chance, depending on who's teaching it, that they might actually return and talk about stuff like this. If you're trying to find maximum minima, this is a great application of the 2 different subjects. And properties of this matrix are related to whether or not you have maximum minima. Another way of trying to look at what we're doing is this is generalizing f prime of 0 times x. Zero. How does f prime of 0 generalize? Well, f prime, oh, that's just the gradient. And x, that's just the point x comma y. So the connection should just be the dot product. How do I generalize f double prime of 0 x squared over 2 factorial? How does that generalize all of the stuff over here? Well, the problem is f double prime, this is going to be a matrix of derivatives. And so how do I have a matrix act on a vector? Row vector, matrix, column vector actually gives me a number. And so you view this as 1/2 x, f double prime of 0 x. And if you write it like that, this then generalizes to something of this form. If anybody here does physics, you have similar issues with how do you generalize formulas from classical mechanics to quantum mechanics. And the problem in quantum mechanics is operators often don't compute. And so the order matters, and you have to look at how do you deal with all of the stuff in play together. So I hope we all understand that we don't really want to do this. And this is only going up to degree 2. Now for degree 3, what the hell is that? It's beyond the matrix. We now start getting this kind of tensor. So let's just erase all of this. And it's good to know that it exists, but we don't want to do this. I'm going to show you a trick now that works for almost every function you need to deal with. Okay. So let's say I give you the cosine of xy, and I want to find the Taylor series. So the stuff that I just erased will give us a procedure to calculate the Taylor series of degree 4. So I want the degree 4 Taylor series. I'm going to let u equal x times y. And I will study the cosine of u. Do we know the Taylor series for the cosine of u? Yes, it's in fact still on the board. Right? There's a reason this hasn't been erased. This is just 1 minus u squared over 2 factorial plus u to the 4 over 4 factorial. Here's my Taylor series for cosine of u. So then the cosine of xy would just be 1 minus xy squared over 2 factorial plus xy the 4 over 4 factorial, and so on and so on and so on. Yes.
You write like the approximate instead of like the equal sign?
Well, I have the dot dot dot. So because I have the dot dot dot, it is
equal.
Because I'm keeping all infinitely many terms.
But didn't you say that some don't converge?
So for cosine and sine, for these functions, they do converge. There are some strange functions like e to the negative 1 over x squared where it does not converge. So this is a situation where it does converge, and this is legal. So I want to look at the degree 4 Taylor series. What do I get when I square xy? So this is going to be 1 minus x squared y squared over 2 factorial. What about x to the 4th, y to the 4th? What's that going to do? What do I get when I have xy to the 4th? Yeah, what degree is that going to be? 8. So the answer is just 1 minus x squared y squared over 2 factorial. So this is a degree 8 term. I'm done. See how much faster this is? This is much better than trying to do all those partial derivatives. And this is a general principle of mathematics. Reduce a complicated problem to a simple one, or to multiple simple ones. If we know the one-dimensional Taylor, we do the one-dimensional Taylor, and then we just hopefully are in a situation we can plug in If I had u equals 1 over x squared, that would be very different. That's a strange bad function. What if I give you cosine of x squared plus y? What would we take for u this time? X squared plus 1. And so it would equal 1 minus u squared over 2 factorial plus u to the 4 to the 4 factor minus, and so on and so on. So this is 1 minus x squared plus y squared over 2 factorial plus x squared plus y to the 4 over 4 factorial. When I look at x squared plus y, am I going to have any terms of degree higher than 4? So when you expand x squared plus y squared, you're going to get x to the 4 plus 2x squared y plus y squared. So this is only going to have terms of degree up to 4. What about x squared plus y to the 4? I look at x squared plus y, x squared plus y, x squared plus y, x squared plus y. I have 4 terms. Is it possible, when I expand this out, to have something that's a degree 4 term? If so, what would that degree 4 term be? Y to the 4. If I choose y every single time, if I choose even one x, and even if I choose the other 3 to all be y's, it's degree 5. When I get the next term, the x squared plus y to the 6, it doesn't matter what I choose. I'm always going to have at least a degree 6 term. So the answer, in this case, would be 1 minus x squared plus y squared over 2 plus y to the 4 over 4 factorial. And so that would be the degree 4 Taylor series expansion for the cosine of x squared plus y. If you want, try to calculate the degree 4 expansion by taking all the partial derivatives. And very quickly you'll realize you don't want to do that. So the idea is, if we know the Taylor series in one variable, we can often approximate it very nicely. So you really should know sine, cosine, exponential, probably even the logarithms. These are very useful ones to know. These are the big common ones. Any questions on what we've done? Yes.
Wait, why are you allowed to take out that y to the 4 and not to take out the x to the 4?
When we're looking at this term,
Yeah.
well, because any other factor when I multiply this out is going to be of degree at least 5. And I'm asking you, what's the degree 4 Taylor?
Okay.
So if I actually wanted to know what the answer is, if the exact approximation, I can't just throw things away. But if I'm saying I only care about keeping degree 4 and lower terms, then I don't care about the x squared y cubed term or the x to the 4th y squared term. Because they'll all have too high of a degree. So for the last minute or two, I would just quickly say a few words about just expanding powers in the binomial theorem. So you've hopefully seen the binomial theorem and its connection to Pascal's triangle before. It plays a key role in calculating derivatives. So x plus y, again, is the sum, k goes from 0 to n, of n choose k, x to the k, y to the n minus. And here, n choose k is n factorial over k factorial, n minus k factorial. It's the number of ways of choosing k objects from n when order does not matter. Think of it as choosing student representatives rather than members of the executive committee. If you have a Pascal string, 1, 1, 1, 1, 2, 1, 3, 3, 1, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1, if you look at x plus y to the fifth, these give you the coefficients of the terms. It's x to the fifth plus 5x to the fourth y plus 10x cubed y squared plus 10x squared y cubed plus 5xy to the fourth plus 1y to the fifth. And there's a nice reason that the combinatorials come up. If I give you x plus y to the fifth, then x plus y, x plus y, x plus y, x plus y, x plus y. If I multiply that out, I'm going to get things in terms of x's and y's. If I have 3 x's, how many y's do I have to have? 2. If I have 4 x's, how many y's do I have to have? I have to have 1. So if I have k x's, I have to have 5 minus k y's. How many ways can you choose k factors to have your x when you have 5 factors? So I want to choose k of the 5 factors to be x. How many ways can I do that? 5 choose k. So once I choose k factors, I have 5 minus k factors left over. I have to choose all of those factors to be y's. So I have to choose 5 minus k objects. What's 5 minus k? Choose 5 minus k. 1. Really, I should have over here n minus k choose n minus k. But because that equals 1, we don't bother putting it in. But really, when you're looking at the formula, there really is a 1 lurking there. But when there's only n minus k objects left, and you have to choose all of them, there's one way to do it. I have 6 objects. I want you to form a group of 6 people from 6 people. How many groups of 6 people can you form? 1. A lot of times you can prove things by story. So if you do some algebra, you would see that n choose k is the same as n choose n minus k. Anybody ever read the Sneetches by Dr. Seuss? There are 2 types of Sneetches on beaches. There are those that have stars on their bellies, and there are those that do not have stars on their bellies. What can you conclude we learn by the end of this story? It starts off, trying to answer who are the best Sneetches, those with stars or those without. What do you think the conclusion is at the end? Doesn't matter. All Sneetches are equally good. It doesn't matter if you have a star or not. And so the Sneetches go through some painful lessons as they learn this. But for a while, there is real discrimination between those that don't have stars and those that do have stars. Imagine I have n Sneetches and I choose exactly k of them to have stars on their belly. What's that the same as doing? If I choose k to have stars, it's the same as to not have stars. So if you're choosing k people for something, it's the same as excluding n minus k people from something. And that's why you can just say, by story, n choose k is the same as n choose n minus. You can also do the algebra, and this would be n factorial over n minus k factorial n minus k factorial. What's n minus k? That's just k. And so that's the algebra proof. But for more involved things, this gets better. All right, so this is a good place to stop. On Monday, we will start our review. And then there's no class on Friday because of Mental Health Day 3.